This video on Laurent Series is motivated by one simple question, and it's written here in pink. So we know that functions that are analytic inside a disk have a power series inside that disk. But what about functions that are analytic only inside an analyst domain? And if you remember what an analyst domain is, it's basically like a ring or a donut. It's this, but it's only the inside, so it's excluding this hole right here. So if a function is only analytic on that area right there, does it still have some kind of power series or some kind of analog to power series inside that analyst domain? Well, that's what this video is going to try to tackle. So how we're going to do that is we're going to first fix some z in the analyst, modulus z minus z naught less than r, but bigger than small r. So let's just first talk about what this means graphically. So if we draw our graph, and let's say this is centered at z naught. So this center right here is not going to be 0, it's going to be z naught. So big R will be like this, let's say the radius big R. Small r will be like this, let's say radius like this. So since the modulus has to be greater than small r, but less than big R, we're stuck with this analyst domain. So this is how you define an analyst domain. It's basically like the area between two disks. Okay, so now we're going to be given that. We're going to choose an R1 and a big R1 such that this inequality is true. So let's read this. So R is less than R1 is less than the modulus Z minus Z naught less than big R1 less than R. So this is a lot to take in, but this picture right here captures everything perfectly. So the two green circles I've drawn are small r and big R. And the two orange circles I've drawn are small r1 and big R1. So basically small r1 is something that's bigger than small r, and big R1 is something that's smaller than big R. I know that sounds a little bit complicated, but this picture tells it perfectly. So if this green is our analyst domain, the orange is basically a tighter analyst domain. It's something whose the little circle of it is bigger, and the bigger circle of it is smaller than the green one. So it's like this. Okay, and furthermore, what you need to be true is, remember we fixed some z. This z should fall inside this domain, and you can always find a big R1 and a small r1 such that the z falls inside that domain. Okay, so now what we're going to do, we're going to consider a closed curve. So I've drawn it here, but I will trace it again on this one so we can see which direction it's going. So this is the closed curve. Let's just say we're going to start, so this closed curve is going to travel around the orange parts predominantly. So let's say we start right here at this black dot, which is at R1, the radius right here. So what we're going to do, we're going to go around this orange, we're going to go around this circle with radius big R1. Like that, we're going to go around once, and we're going to go around in the counterclockwise direction, okay, which is a positive orientation because you're keeping the analyst domain always to your left. Now what we're going to do, we're going to go to the smaller circle like this across this little horizontal piece, and then we're going to traverse the smaller circle with radius smaller one once, and we're going to traverse it in the clockwise direction, which is a positive orientation because we're keeping the domain always on our left again, and then we're going to go back like this, and we're going to go back to our starting point. So you see that this little segment right here has been traversed twice, once in the leftward direction and once in the rightward direction, and that's important because that's going to mean when we take the integral of it, it's going to cancel out. So I've drawn that path right here. It's a little bit sloppy, but we see that again. We're going to start here. We traverse the big circle once, and I've left a gap in between just to show the twice traversal of this horizontal piece, but there's no gap in between. So we traverse the outside part once, go inside, travel the inside circle, and then go back outside, and that's a closed loop. And notice something about this closed loop right here. It contains z. This closed loop contains our z. And furthermore, this closed loop is inside a domain where f of z is analytic. So our function is analytic inside the green analyst domain, correct? And since the orange analyst is inside the green analyst, that means that the f of z is analytic on this closed loop and inside the closed loop as well. So because of all that information, we're allowed to use Cauchy's formula, which is going to be the crux of what we're going to do now. So we're going to use Cauchy's formula, which is f of z equals 1 over 2 pi I integral f of w over w minus z dw, and then we do it over the loop that we're using. Now I've drawn two here because our path consists of two loops. Consists of the outside loop and the inside loop. Notice that since we traverse the horizontal segment twice, it no longer matters. It just cancels itself out. So we're just worried about the outside circle and the inside circle. So just to make matters simple, I've just called, instead of writing gamma 1 or gamma 2 here, I've just written big circle and small circle so we can keep our circles in order. So again, it's 1 over 2 pi I, this integral over the big circle, plus the integral of the small circle. And it's plus because they're both in the positive orientation. There's nothing negative yet. Okay, so I've written in pink, the integrals over the line segments cancel, so we don't need to worry about them, which is good. Okay, so now we're going to do some kind of fancy algebraic manipulation. So now for the big circle, we notice we have this term right here. We have 1 over w minus z. We're going to rewrite this. 1 over w minus z equals 1 over w minus z naught minus quantity z minus z naught. So convince yourself that when you work out the denominator, it's still w minus z, because you have this negative z naught plus z naught, so it's still w minus z. So I haven't changed anything. So now what I'm going to do, I'm going to factor out 1 over w minus z naught from this fraction right here, and that leaves me with 1 over 1 minus z naught over w minus z naught. And the reason I did all this is because now this right here is in the form of a geometric series sum. Because remember, geometric series sum is term 1, which is going to be this, term 1, right here, divided by 1 minus the common ratio. So this is the common ratio, and remember, geometric series only converges if the common ratio is less than 1. And in this case, we're going to take the modulus of it, so we can say it's absolutely convergent. So is the modulus of the common ratio written right here? So modulus z minus z naught over w minus z naught, is that always less than 1? Well, that would be true if z minus z naught is less than modulus w minus z naught. And looking back at our picture, is that true? So z minus z naught modulus is the distance from this fixed point z we chose to the center, so the center is z naught, and w minus z naught modulus is the distance from the radius of the outside circle to this center, and that's always bigger. Notice that the radius of this outside circle, which is r1, big R1, is always bigger than the distance from z to this center, because that's how we kind of created that big circle. So since this is always true, this is always less than 1, and this converges. So since it converges, we can write it as a sum. We can write it as the sum, the common ratio here is this, and the first term is this. So all we really have to do is multiply the common ratio by the first term, and then we can put in our k, and then, so we're starting at k equals 0, and we have our sum here. Okay, so convince yourself that this is indeed the sum. Again, how I got this was I put the first term multiplied by the common ratio to the power of k, which is why there's a k plus 1 exponent down here and a k exponent up here, because this is kind of repeated in the common ratio and the first term. Okay, so now we're kind of just we're gonna do the exact same thing for the small circle. So again, we're gonna start with 1 over w minus z, just like we did here, and we want to do a different thing here. So again, we're gonna do this step, and then I'm gonna pull out a negative 1 over z minus z naught, and then what I'm left with is 1 over 1 minus w minus z naught over z minus z naught. And now notice there's a negative here, and using the same technique, I again did the same thing where I instead of I found out the common ratio here. The common ratio is what? It's gonna be w minus z naught over z minus z naught modulus. That's always less than 1. And the reason for that is because w minus z naught modulus is less than z minus z naught modulus. Because now the opposite case is true. Now we're traveling on the smaller circle right here, the small orange circle, which is now purple, the smaller circle right here. And the distance from anything on the small circle to the center is always less than the distance from z to the center. So the opposite story is true here, which is why I did a different algebraic manipulation. But nonetheless, we're left with a new series right here. We're left with a negative series, the negative sum from 0 to infinity of w minus z naught to the power of j over z minus z naught to the power of j plus 1. Okay, so this is the main thing that we wanted. We wanted to get this series and this series right here. So the next thing we're going to do, we had this f of z expression right here, and we had f of w, and we had 1 over w minus z in both of them. Now we have new expressions for 1 over w minus z. We have this expression and we have this expression. So we're going to complicate things, and we're going to plug in those sums into our f of z formula. So we see that this is, even though this looks complicated, it's really the same thing as this expression right here, except I substituted 1 over w minus z as the sums we just found. So those were put in here. Now notice something. Now we have the integral of a sum, which means we have the integral of something plus something plus something. And as we always do, we can split up the integrals of something plus something into the integral of this plus the integral of that plus the integral of the next thing. And so we can write the integral of the sums as the sum of the integrals. So all I've really done here is I've just flipped the integral and sum order, which is okay, because that's how integration, that's a rule of integration that you're allowed to do. Okay, so again, we have it over the big circle, small circle. I've written it again, first summation and then integration in this order. And then we have big circle and small circle. So if you would like, go ahead and convince yourself that each of these is consistent. And then let's go on to the next step. So now this is the end part. So now we have a f1 function plus a f2 function. What's our f1 function? Our f1 function is this one right here. And our f2 function will be this function right here. Okay, so it's this function plus this function. This is f1 function plus f2 function. And the main point we want to note here is that where do the f1 function and the f2 function converge? So just a small thing, I've written the coefficients. So notice the coefficients were really complicated here. They were this 1 over 2 pi I integral f of w over w minus z naught, all this mess in the parentheses. Since it was kind of complicated, I just named them a sub k so we can write it in a more compact form. So here f1 function and f2 function. So notice the f1 function, the k goes from 0 to infinity, and the f2 function, the k goes from negative infinity to negative 1. So the f2 function has all negative exponents, and the f1 function has all positive, or, well, 0 exponents right there. That's the result of the z minus z naught being on the bottom here, but being on the top here. Okay, so we have shortened our a sub k, and we have a new compact form for our f1 and f2. So now let's talk about where is f1 convergent, where is it defined, where is f2 convergent defined. So f1 is convergent where? Let's take a look. Let's trace back to where what f1 is. So f1 was the integral around the big circle, correct? And we said it's convergent. The series converges as long as the modulus z minus z naught is less than modulus w minus z naught. So let's go back to our picture once more. And let's see. So it's convergent as long as the distance from z to z naught is less than the distance from w to z naught. So that means the distance from here, z, to the middle is less than the distance from the outside circle to the middle. Now z can get super close to the outside. It can get super close to this green circle. And we can always still choose a new orange circle that's still farther away from the z, but still behind the green circle. So this will always be true. But as soon as we pick a z that's outside, we can't do this anymore because we can't pick an orange circle that's out there because it's no longer inside the domain where f of z is analytic, because f of z is only analytic inside the analyst domain that's green. So we can't choose anything out there. So as soon as we choose something out there, it's no longer defined. This series no longer converges. So the rule for convergence is that the modulus of z minus z naught has to be less than r. So this is f1 is convergent when modulus z minus z naught is less than r. So on the same note, the second function, f2, this is based off of the small circle. So using the same logic, we can say this is analytic when the modulus z minus z naught is greater than small r. So since this is analytic when it's less than big R, and this is analytic when it's greater than small r, if we add the two functions together to get a new function f, okay, because that's what f is just the sum of this and this, which turns out to be the sum of this one and this one, which we just split up as f1 and f2. So when we add them together, this sum can only be analytic when both of these conditions are met. So that means when modulus z minus z naught is less than big R, but also greater than little r, which is exactly the analyst domain that we were talking about. So since this is a function which is only analytic inside an analyst domain, so this is represented by this power series, we call this a Laurent series. So a Laurent series is a special type of power series that's only analytic inside an analyst domain. So just a quick note on analyst domain. Analyst domain can be anything from a disk like this to a domain where the only thing that's removed is this point. So we used to call this a punctured disk because it's the whole disk minus the center. This is technically still an analyst domain where small r is just equal to 0. So these are all analyst domains right here. Okay, so we have this Laurent series, and the last thing we'll talk about is that this is super easy to find for poles. So you might think that this discussion right here is very complicated. We have to do all this work. Well, usually when we have to do the work just for poles, it's really, really easy. For example, we did this example in the previous video where we had to find the power series of e to the z over z minus 1 to the power of 3. And we did that simply by writing this power series. But what we didn't know then, but which we know now, is that this is just a Laurent series, right? Because it's just a series with negative to positive powers, exponents for z minus 1. So we have here z minus 1 to the power of negative 3, z minus 1 to the power of negative 2, z minus 1 to the power of negative 1. Here is z minus 1 to the power of 0, z minus 1 to the power of 1, and so on. This is a Laurent series right here. And we didn't have to do all this fancy work to find it. So if we have poles, it's usually easy to find. So in fact, that is the Laurent series. And the last definition we'll talk about is something called the principal part. So the principal part of a Laurent series is just all the terms that have negative exponents. So we see here that this is z minus 1 to the negative 3 to the negative 2 to the negative 1, but the next term is to the power of 0. So 0 is not negative, and in fact all these on this side to the right are not negative. They're all positive powers. So these three terms are the principal part of this Laurent series. So this will be important later on, but just remember that principal part is all the terms in the Laurent series where the exponent is negative.